Very excited to introduce you to Krste Asanovic, co-founder and chief architect at SiFive. Please give him a warm round of applause.
Okay, thanks everybody. Excited to give you this talk today about what's been happening with AI and RISC-V at SiFive. So just to start out, the main topic today will be this interface, VCIX, that we've introduced. I'll be talking about the X280, which is a product we've had out for over a year, but we recently refreshed it. And today I want to talk to you about some of the interesting use cases some of our customers have been coming up with. Very excited today that not only we get to hear from me, but you also get to hear from Cliff at Google, who will tell you his ideas on how we might possibly use something like VCIX in future AI products. How might that go about? So I'm co-founder and chief architect at SiFive, also RISC-V chairman of the board, and still a professor at UC Berkeley. And Cliff is probably well known to this community as one of the main architects of the TPU, and also one of the important project MLPerf. He's one of the co-founders there. So let's talk about the X280, just a refresher, and also there's some new features we just introduced on the X280. So the X280 has a 64-bit applications processor plus an expanded vector unit. So our intelligence line at SiFive, you can view this as full-featured processors with a big emphasis on vector computing, on highly parallel, data parallel computation. So the Scalar core, 64-bit, 8-stage dual issue in-order pipeline. We have a completely RISC-V Vector 1.0 ratified standard compatible vector unit on the side of it, implements the full spec. It has 32 512-bit vector registers. And the RISC-V standard allows you to gang together multiple vector registers to make a longer vector. Up to 8 can be ganged together, so you can perform a single vector instruction, can perform an operation on up to 4,096 bits. This helps you reduce power, increase utilization on codes where you have longer vectors. Now, in addition to the standard vector instruction set that we fully support, at SiFive, we've added some custom instructions to help with some AI workloads. And so those are the SiFive Intelligence extensions. And these include various forms of matrix multiply, including bflow16 support, and also various forms of quantization instructions, which help in converting between the various data formats you find in these AI kernels. Now, one interesting thing about this core, it heavily emphasizes vectors, but it also has a full RISC-V software stack support. It's a full applications processor, including can run a hypervisor. So this is a full Linux-capable core with a wide vector unit on the side. It's very efficient. It's a efficiency class processor, but with full application processor support. And in particular, it's going to support the upcoming RISC-V application profile, RVA22, which will be the standard model for future distros to target. So it also supports up to 48-bit virtual memory space on the core SV48. And we've just announced we can now support up to 16 cores in a cache-coherent configuration. So you can have 16 cache-coherent cores running full Linux or even hypervisor across the space, but each of those cores has this big, wide vector unit on there. So the memory system is high performance. Every core has a private level 1 caches, but also a private level 2 cache. And the way the core is designed, the vector unit streams directly from that level 2 cache. So the vector unit is decoupled from the Scalar processor, but typically vector codes have large vector data working sets, and so we designed this core that the vector unit is directly streaming out of that private L2 on each of the cores, and then all the cores share a level 3 coherent memory system. The system also has a prefetching as well to increase bandwidth for codes where you may not have vectorized the code already, or just other kinds of code that improves the utilization of the memory system with a full stride-based prefetcher. So we've also been improving software compilers on this core, so you see an uplift in the performance numbers coming from improvements in the compilation for this class of processors. So in terms of spec, our spec numbers grew. We're starting to see some auto vectorization coming in there into our spec numbers. So a very capable applications core, but with a very wide vector unit optimized for high throughput on the side and supporting large cache coherent multiprocessor configurations. Now, I just want to talk a little about the AI acceleration we've added to the X280. So if you just start with, this is one example we've walked through, which is MobileNet. Just using the scalar ISA, you get a certain level of performance. And as you expect, when you employ the RISC-V standard vector extensions, you get a big boost in throughput. In this case, 24 times faster on the X280 once we tune for the RISC-V standard vector instructions. But to go further than that, we added the additional matrix multiply quantized instructions, and we get an extra 6x speed up on top of just the optimized vectorized code, adding those AI ML instructions. So this is quite nice, and the X280 by itself is quite capable for running smaller inference tasks at the edge, for example, where it can completely replace, it can be the applications processor and the inference engine for smaller workloads. Now, we introduced the X280 last year, and we were very surprised at the uptake. We were very pleasantly surprised. There's a lot of interest. A lot of customers have licensed the X280. And one of the interesting things that we hadn't predicted that we saw happening with the X280 was that customers were using it as a companion core. So the X280 has a bunch of features to accelerate AI ML, but it's not a kilotop, petatop monster, right? It's not that massive AI accelerator that lots of people are interested in building. But people who build those big engines suddenly realize there's a lot of complex compute I need to do that my big accelerator doesn't really know how to do. I need a very full-featured software stack as well to run the rest of the code that's not the kernels that sit on my big accelerator. And so a lot of our customers, they'd license this core to sit next to their large AI accelerator. So this was basically providing all the maintenance code, the operating code, and running all the kernels that the big accelerator couldn't do, or people realized later they had to add some extra functions. This has a vector core, so we can run them reasonably fast and support that big accelerator. So this model of a companion core we saw with a lot of our customers. They started licensing it, but they also started, once they saw that use case, they saw, well, things could be a lot better. Because initially they were just using this as attaching their accelerator as a memory map device on the side of the X280. But that's sort of hundreds of cycles away by the time you take into account bus matrix overheads, memory system overheads to get to and fro. And it kind of works for larger offload of larger chunks of work. But when you want to have a more tighter coupling, it wasn't really that great. And so the customers came to us asking for a much tighter interconnect between the X280 and the accelerator they're going to be adding, a much, much bigger engine that's going to be sitting on the side. So working with the customers, we came up with this new interface we call the Vector Coprocessor Extension Interface, the VCIX for short. And so what VCIX does is let you plug in your accelerator directly into the vector register file of the X280. So now you can communicate with the order of a few, maybe 10 cycles. On the order of 10 cycles, you can get data in and out of the vector registers directly to the accelerator and back again. So that's the model. Now, in addition to attaching accelerators, you can also use that same interface to add complex instructions. So maybe you don't view this as a huge accelerator on the side, maybe just adding instructions that match your own custom needs for some application you're doing. Maybe some color conversion, FFTs, other kinds of custom instructions you can easily add on the side using this VCIX interface. And they operate almost as if they were additional vector instructions operating in and out of that vector register file, right? So this gives you increased performance, much greater data bandwidth in and out because you're going directly into the vector register file, much lower latency, and also simplifies the software because now that coprocessor is being driven directly from the instruction stream of the X280 and synchronous with that instruction stream. So dive down a little more into the details. So this is just showing you where VCIX is in the X280 core. So we have the scalar core with the vector registers on the side. So we have 32 512-bit vector registers in the X280. VCIX connects directly to those vector registers, but also to the scalar instruction stream of the processor. And so over that interface, you can be shipped instructions that are coming out of the RISC-V instruction stream, plus you're getting data that's being shipped in and out the vector registers. And on the X280, we can ship 1024 bits over to the accelerator per cycle and retrieve 512 bits per cycle, every cycle sustained, over that VCIX interface to that attached accelerator. So this is a very high bandwidth, very low latency path directly coupled to the instruction stream of the X280 scalar processor. So as you can see, when you're trying to offload some functions to the big accelerator, but then handle other things with a flexible software in the X280, this provides a very smooth path. Right? You call out to the function accelerator, data shows up in your vector registers. You can then use the standard RISC-V vector operations or the SiFive Intelligence X280 to work on that data right there in the vector registers. Right? And this is much higher bandwidth, much lower latency than going through a memory mapped interface to get to your accelerator. So the advantage here is you can bring your own coprocessor into the RISC-V ecosystem, and you get that full software support, including, remember, this core can run full Linux, including hypervisor, full virtual memory, and you have cache coherent support across 16 of these cores in the current product. So to support the X280, let's talk about the software support for the X280. So the sort of spectrum of software support, different levels of effort and quality of results, obviously. You can go all the way down and hand-tune your code in assembly code. What's nice about RISC-V vectors is that assembly code, you can make it portable across many different vector implementations. So you spend that cost once of vectorizing the code, and it's going to perform pretty well across different families of vector processors. As well as coding assembly, there's also the standard intrinsics. So you can code one level up and in C level, but using intrinsics, which will map quite closely down to the RISC-V vector instructions. And if you're used to programming more in C, this will help, and the compiler will take care of things like register allocation, detailed instruction scheduling at that level, but you're still selecting what kind of function you want to do using those intrinsics. Now, we understand a lot of customers have existing code for other architectures, and to help them move that over to RISC-V vectors, we introduced the product Recode, which helps you take that code, intrinsic code written for a different architecture, and we'll recompile it to target RISC-V vectors. And the model here, you won't get perfect performance on that code, but it allows you to quickly port the code over. So you can then focus your energy on the few pieces of the code that are really performance critical, while the bulk of the code came over with a reasonable performance over to RISC-V vectors. We're also working on auto-vectorizing compiler, and as you see, we're starting to get initial results there. We're even on spec-int, we're getting speed-ups from using LLVM-based auto-vectorizing compiler. And so, auto-vectorizing compilers are not perfect tools. In practice, they help you, but you have to understand what it's doing. And typically, you go in and restructure your code a little bit to help the auto-vectorizer work. But that's there and improving steadily. And also, of course, we have prepackaged, optimized libraries where our experts have coded those routines directly for X280. And that'll typically give you the highest performance if your application can map directly to an existing library that we already have. Okay, so at this point, I've introduced the X280, talked about where the VCIX came from. Very happy now to hand over to Cliff to explain how he might imagine using something like this.
Thanks, Krste. Is that the clicker? Thanks. So, hi, I'm Cliff. It's great to be back at AI Hardware Summit in person, and thanks for the introduction as well. I guess I've worked a little bit on TPUs, and so I thought I'd start with a slide about a TPU, which is representative of the kinds of accelerators we are building or interested in building at this summit. I stole the graphics for this slide from my colleagues Thomas and Nishant when they presented TPU v2 and v3, and the schematic is kind of basic about what's in a TPU, right? Of course, it's got a scalar unit, a vector unit, and a matrix unit, where the matrix unit with its systolic array is perhaps the source of the ridiculous numbers of teraflops or petaflops that we're delivering. There's a pretty standard on-chip SRAM with vector memory. There's near-chip HBM integrated in package. We invest in high-performance interconnects these days to link thousands of these chips into pods. And there's still a host interface back through PCI Express these days, soon CXL, to talk to the rest of the world and all the file systems and the Google data streams in our data centers and so forth. So, but what I wanted to contrast about this diagram is we build all of this stuff from scratch. And 9 years ago, when we first started building TPUs, there was very little other choice than to build it all from scratch. Right? You really couldn't crack open somebody else's processor and use that as a baseline. It was hard. Machines were kind of monolithic. Nowadays, we're in a more IP-oriented universe, and it's possible that we don't have to build everything from scratch. And so if you look at what's in a TPU, the actual unique bits that are where Google focuses a bunch of its innovation are in the network and in the systolic array, the bits that I've highlighted in red. The rest of it, like HBM, is a commodity originally pioneered by the wonderful GPU people. SRAM on the device is something that TSMC and other foundries produce as part of refining their processes. Scalar and vector technologies are relatively well understood technologies. I think Krste is one of the pioneers in the vector computing area and has built beautiful machines in that way. But should Google duplicate what Krste has already been doing? Should we be reinventing the wheel along with the matrix multipliers and the interconnects that we already have? It'd be much, much happier making for us if the answer were no. If we could focus on the stuff that we do great, and we can also reuse a general purpose processor with a general purpose programming stack, integrate that into our future accelerators. And I think Krste was talking about compilability and Linux and so forth within the RISC-V operating system, or sorry, RISC-V ISA and operating system area. I think that the distinction to draw is actually general purpose core versus accelerator. One of the themes you've seen in the panels today has been, how do you program these darn things, right? Like, which stack of frameworks and various different bespoke libraries and so forth do you cobble together to make it easier for programmers to use this machine? How about a general purpose CPU approach, right? CPUs have this wildly diverse ecosystem. You want to run Python? Run Python. Run it right next to your accelerator core. And so I think the promise of VCIX is to get our accelerators and our general purpose cores closer together, not far apart across a PCI Express interface with thousands of cycles, microseconds of delay, but right next to each other. Where Krste was just telling us about hundreds of cycles through on-chip cache, tens of cycles through vector register access. And so I don't actually know how to get any closer than what VCIX gives us, than tens of cycles through vector register access. So, almost done. I thought I'd go a little bit into technical detail about the division of labor that is both technical and business between what SiFive is bringing to bear here and what Google is able to then focus down on. So Krste outlined the VCIX interface. He said companion core, I say base core. I don't think we need to fight about that. I think it's just a matter of perspective or which side of the interface you're on. But 64-bit scalar machine with a great sequencer and a known ISA and a compiler. A vector unit, which goes through the L2 layer. So it's a wide path to memory, not a narrow, fast path to memory. The wide path to memory is exactly what we want to drive an accelerator, right? 64, I think it should be bytes, right? 512 bits per cycle to memory until the cows come home. That's the kind of memory plumbing you need to have to drive these accelerator-like units. And another nice virtue of the division of labor in VCIX, when you think about the RISC-V architecture, one of its great positive points is its customizability, its extensibility. But the place where technical reality meets up with business reality there is if you want to extend the ISA of a SiFive core, you have to ask SiFive to change their decoders, and that kind of breaks the IP distribution model, right? Like they have to crack open the decoders and add your particular decodings and then DV that and deliver you that thing. One nice thing about the VCIX interface is that they don't have to crack open the decoders. Instead, there's kind of an overlay sub-ISA. The VCIX interface has a relatively rich set of 20 or 30 instructions, which mostly are concerned with sending things and receiving things back to and from the accelerator piece. You're free to interpret those as you want. And so whether this push and pop combination with this set of flags set on it means matrix multiply, or whether it means butterfly, or whether it means video compress, it's kind of up to you. And so there's enough richness there that we find we can control some of our new MXUs with it just fine, and I think other people in other areas can as well. RISC-V extensions, software toolchain I already spoke about. Pushing and popping is kind of how we drive our MXUs in TPU land already. There's more technical detail probably in the specs about the division of labor in the VCIX interface. Part of what we negotiated with SiFive in dividing the labor is that these MXUs of ours are incredibly long latency. MXU, sorry, means matrix multiplication unit. If you look at a systolic array matrix multiplier, it's kind of got this huge pipeline depth to it. Like whatever the side length is, it can be twice that side length in cycles to like just shift everything through. If you plug that into a standard processor design, your scoreboard and your out-of-order engine die because you do a two-source, one-destination operation, and then the destination is tied down for 100 cycles. Part of the VCIX division of labor is that we took on that complexity ourselves. Like Google knows how to deal with that latency. Google already writes software to drive these super long latency kinds of things. And if you're building a neural network accelerator, that's fundamental to your business as well. SiFive doesn't worry about 100 latency operations. Instead, we divide the labor up and make it so it's a nice technical and business division. Okay, push pop I talked about, tight coupling. Yeah, I think last thing I'll wrap up on is the programming model piece. I've been telling friends, I think I've kind of been an accelerator heck for the last 2 decades of my career, where when you build the accelerator, all you have is the accelerator primitives. And so in TPU-v1, if you wanted to move a piece of memory from point A to point B, what do? You don't load it and store it. You actually do a matrix multiplication on it with an identity matrix, and it takes you like this horrible sequence of code instructions just to get that to work, because there's no standard library where somebody has built you memcopy. On a CPU, you just say A equals B, or memcopy from pointer P to pointer Q, and it just works. With VCIX-based general purpose cores hybridized with our matrix unit, you can actually build a machine that has a little bit of having your cake and eating it too. All the performance of the MXU, all the programmability of a general purpose processor. And I think that future is a rich one and possibly a way in towards building much more programmable future machines. So I'll pause there. Krste, I think this is, okay. Maybe we should plant some seeds about possible questions. You could ask about like why SiFive and why RISC-V and so forth, and what other alternatives we considered, but I think we have a little time for Q&A.